Hello and welcome to the instructional video for measuring the mass of the Earth lab. Here, we're going to use a simple pendulum to, you guessed it, measure the mass of the Earth. So here I've got some everyday objects. I've just taken a charging brick for a computer and I've clipped a piece of yarn onto it, and that yarn is attached way up high to this workout equipment. You want your initial string length to be as long as possible because you will get better results if your string is longer. So what we're going to do here is have my assistant, hello assistant, do a release of the pendulum so we can see what that looks like, okay? So go ahead and pull it back. You want to pull it back just a small amount, all right? And then there we go. All right. So when you release it and start it swinging, you want to make sure that you time the swings. And you can see that, here, me holding the camera, I haven't started the timer. But let's go ahead and start it. What's very important is you want to start the timer at the very instant that the swinging object, our pendulum, by the way, the white thing at the end, we call that the bob of the pendulum. So you want to start right when the bob is at the top of a swing. And one swing is only completed when the pendulum gets back to where it started. Okay? So for example, start, stop. See how that's one complete swing? Let's do it one more time. Start, stop. See, one complete swing. Now, we want to have a measurement or measurements of 10 swings at a time. Let me show you the data table right down here. This is just a printed version from your lab, question 2. So you can see that we're going to have different length strings, okay? And we're going to measure the time for 10 periods. So 10 of those complete swings that I was just talking about. Okay, and then we're going to do that a total of 5 times. Each one of those is the trial. That's why there's 5 rows. All right, can you go ahead and start it swinging one last time for me? Now, it's not a big deal that it kind of keeps swinging and gradually slows down because the time it takes to do a swing doesn't really change, even though the pendulum is gradually losing energy and coming to rest. The time basically doesn't change. And it doesn't matter what angle you release it from. It's actually independent of the angle. It only depends on gravity and the length of the string, okay? As long as the angle is pretty small. And that's part of the advantage of having such a long string, okay? Small angle, right? Okay, so let's go ahead and just show a timer real fast, okay? So imagine I'm starting at the top of a swing, okay? Maybe I can hold this up and do that. All right, so we imagine that we're going to start. Can you do one last thing for me? Amanita, can you go ahead and hit the start button when I tell you to, right there on the iPad? Okay. All right, so you gotta get a little bit closer so you're ready when I tell you. Okay, yeah. Start. Nice job. Okay, so that's 1 swing. Now it's in 2, 3, 4, 5, 6, 7, 8, 9, 10, all right? And you would need to be ready to hit stop. Of course, you won't be holding a camera. So let's imagine we did that right away. So it would be, some number of seconds later, maybe about 27 seconds, okay? And that's the number you would write right there in this cell right here for the time for 10 periods, because that was how many seconds it took to complete 10 complete swings. And the period of time is called the period, the event is called the swing, okay? So you need 10 of those as you saw in the video, okay? And you get better at counting them and so on. That's the advantage of doing multiple trials, okay? Now, here's the last thing. You have to measure the length of the pendulum, okay? So you would simply get out your measuring tape and you'd measure the distance from the center of the object that's swinging, okay? So right as close to the center as possible, right up to where your string, or in my case, yarn, is tied off. So you need what's called the pivot point. So it'd be right at the point where it's tied off. So you would need that distance all the way from the pivot right down to the center of the bob, okay? All right, so that's it for kind of the data collection. Obviously, you're gonna have different length strings, right? Because of course that would just be your length 1. And then after repeating, 10 total swings 5 times, okay? So that's a total of 50 swings, but just 5 trials. Then you're going to have a different length. My advice here is start long and go gradually shorter. So if your first length was 2 meters, maybe your next length should be 1.7 meters and then 1.4. But don't get too short, nothing like 30 centimeters. Keep it as long as possible. Okay, so stay tuned for the second part of the video where I talk all about the data analysis. All right, see you then.
Hello, and welcome to the second half of the instructional video here for Lab 3, all about measuring the mass of the Earth. So in the first video, I went over some tips about how to actually collect the data. And you saw an example of the setup that involves string and a homemade pendulum. Okay, I talked about the advantage of using small angles in a long string and how you want to let the pendulum swing multiple times. Okay, well, we'll skip over the bit of the theory. I want you to obviously be making sense of this as you go through the lab, but let's get down to the nitty-gritty here. I'm going to go through each of the questions, some more briefly than others. Of course, you're going to want a picture of your setup right here that you're just going to insert into the document before you submit. But let's take a look at some made-up data. Now, this is made-up data, but it's based on what I would expect real data to be because I calculated some things backwards and so that we could have realistic data. Okay, so let's talk about the analysis. The actual process of analysis in this lab doesn't involve using any Excel. We don't have the program Excel. We don't have to use any spreadsheet calculations. All the calculations we can or need to do, we can just do with a normal calculator. Here I have Desmos open, and we'll be doing our calculations over there. Okay, so let's take a quick look at what is the data I collected. Now I only have imaginary lengths or imaginary data for 3 different lengths. Okay. Just so to show you an example, 3 will certainly be enough to draw a graph and draw a line that connects the dots of that graph in one of the next questions, in fact, in question 4. Okay, but in your data, you will need to also have values for lengths 4 and 5. Okay, so taking a look at this, you can see that the lengths that I chose are 2 meters, so about 6 feet, 1.85 meters, and 1.5. These two are kind of close to each other, but regardless, that's fine. Just do the best you can. Now, here are the 5 trials. You're literally just going to write those numbers there, just identify the trials. Now, here is the actual data. This is how long it took for 10 swings to be completed. Okay, so essentially, I let that pendulum bob swing back and forth to complete a full what's known as an oscillation or a full swing, which is when the pendulum bob gets back to where it started, and that happened 10 times. And I just measured the total time for all 10 swings. The advantage of doing that, of measuring 10 swings instead of just 1, is you have less of a percent error, like less of a proportional error from the inevitability of not quite hitting start and stop on your stopwatch exactly when the swings start and stop. Okay, and that to say that there's going to be some variation in the period of the swing because of course the pendulum is gradually slowing down. Well, that effect is actually much more minor than would be the proportional effect of just stopping and starting the stopwatch for just 1 swing. So it's a real advantage. So we're saying that it took about 28.2 seconds, right, for the first trial and so on. So the first calculation we need to do, we're going to fill in this cell right down here, is simply an average. Okay, so I want to call this, let's see, so this is our average for T, and this will just be T1. All right, I'm just going to label some variables here, right, which is a nice thing about Desmos is you can just set up these variables. Okay, so T1, and this is going to be the average for 10. Okay, so this is, so, well, calling it 10, should I just call it 10 T1? Sure, we'll just do that. All right, well, how do I want to label it? For now, I want to call this something other than T because, of course, the first cell we need to fill in is the 10T. So what about we give this the letter, go back over here, we'll call it N, okay? So N is all of them together, like N is like a counting number, okay? So let's just plug in the actual values. So we have our 28, I want to make this a little bit easier to work with here. Okay, so 28.2, and then plus 27.8, plus 29.2, okay, and then plus 29, all right, plus 28.4, and your data is going to look a lot like this, okay? Not exactly the same, of course. Okay, so that's all of them together, but of course I have to divide by 10, okay? Oh, not yet, sorry. I have to divide by 5, right? Now, I was confusing myself there because here I'm taking the average. So I divide by the number of trials, not by the 10 that represents the 10 swings, okay? So in other words, this is the average time it took for 10 swings to be completed. So the average time for 10 periods was 28.5, all right, seconds. And I'm just showing 3 significant figures here, so I'm not showing the 0.2. It's fine either way. I'm not picky about that at all. Just don't include too many, but 4 would be fine as well. Okay, and then of course I want to then say that T1, all right, the name I didn't want to give to that first variable because it was not in fact the period, all right? So T1 is just going to equal N1, and you don't have to use this kind of notation and work in Desmos. You can do it on just a normal calculator. But I do find this somewhat helpful, right? So of course, when we divide by 10, we just get 2.85. Okay. Now we could have done that, in our heads because dividing by 10 is just moving the decimal place over 1, and I think I'll go ahead and do that the next time. Okay. So let's then just go ahead and combine steps essentially. So we're going to go and have call T1. Oh, this would be T2, excuse me, because it's the second trial. Not the second trial, but the second length. So the subscripts here refer to the length. So that was everything for length 1. Now for length 2. Okay. And then this is just going to equal our average. Okay. And with averages, you just add all the values together and divide by the number of values. So 26.1 plus 26.5 plus 27 plus 26.8, right, plus 26.4. So the values I chose here, kind of represent the type of, imperfect data that you might really see. Divide by 5, okay, so that would be the 26.56, okay? And then, of course, I need to divide by 10. So if I divide by 10, that's the same as just dividing by 50. So we get 2.65, all right? Actually be 2.66, all right? And you can see there on the average for the 10 trials, I did in fact include 4 significant figures, no big deal. All right, let's do the last one. Okay. And that's what I meant by combining steps, where I divided by both 5 for the number of trials to get the average, and then divided by 10 for the 10 swings to get the time for a single swing. So let's do it for our third length. All right. And the only reason I combined steps there was just so we could get onto the other parts of the lab. All right. So, of course, you can skip forward if you get the idea, but I do want to get all 3 values because we're about to graph them. So 24, and then plus 24.6. You don't need the 0.0 that I just included. Most of the time I don't include that, but I already put the decimal in, so I decided to keep it. But there you go. See, with the 23, it's fine. 24.5. All right, and then we'll do a divide by, we're going to divide all of that by 50. Remember, 10 for the number of trials, 10 for the number of swings, 5 for the number of trials. So 2.41, okay? So this would be, up here, this would be 24.1, all right? And then here, this would just be 2.41. Okay, so now finally we're going to get to the, not just averaging things, not just the math side of it, but the actual, the physics that applies to astronomy, because of course we're talking about planets here, but we're applying some techniques of physics to, work with measuring the mass of the planet. Because, this doesn't just have to be Earth. You could use a simple pendulum, which is, what this is called, where you got all the mass at the end of the string, and the string is assumed to be massless. It's called a simple pendulum. But you could use such a device on any planet if you happen to find yourself on some other planet, and the time it took for it to swing could then be used to calculate the gravitational acceleration on that planet, because gravitational acceleration varies between planets and varies between moons for that matter. Okay, so now let's calculate this value, t squared over 4 pi squared. Okay, so we're going to do it for each one. All right, so I'm going to have one calculation for T1, that corresponds to length 1, and so on for length 2 and length 3. All right, so let's go ahead and show that. Okay, so this is just going to be the first one. We'll take our variable, T, all right, 1, and we're going to square it, which is part of the formula. That's all explained up in the theory in the start of the lab, and then 4 pi squared. Okay, so the value we got here is 0.206. Okay, what are the units? Well, the period was seconds. Everything here in the denominator are just constants. These don't have dimensions, which is to say they don't have units. So since we're just squaring time, it's just seconds squared. All right, so there we have it. All right, so let's do the same thing for the second length, which would be T2. Okay, all right, T2, there we are. And then square it. Okay, looks good. And then just, of course, divide by 4 pi squared. Okay, pi squared. Okay, so this one then would be 0.179. Notice I'm following the rules of rounding. That rounds, the 8 rounds up to a 9 because 6 is bigger than 5. 5 also rounds up. Okay, that is, a good thing to do. And actually here, I can make this so slightly faster because I can copy this formula down here and then just actually click right on in the tablet here, or you could, you could obviously do it on a PC with just using your cursor. And I'm just going to change that subscript to a 3. All right, since I have such a variable, t sub 3, saved. All right, so there we have 0.147 square seconds. Okay, and of course, they're all the same lengths, right? So you would just, whatever value you have, right, that's the same length. You're just doing an extra calculation in this next table. Okay, so there we go. That's everything for working with the data, all right, in terms of taking the average of the 10 swings and then the average of one swing, okay, and then calculating this value. The whole reason that we're calculating this value is because we're now going to create a graph, and the advantage of having this value, which is actually going to be the values on one of our axes, well, it lets the slope of the graph be precisely gravitational acceleration. This concept g, right, little g, now, and on Earth, that should be 9.8 meters per second squared, the rate at which objects speed up as they fall. That's the rate at which their velocity changes. You gain 9.8 meters per second of velocity for every 1 second you're in free fall. That's what gravitational acceleration means. And it defines the whole idea of feeling heavy on a planet and the concept of weight, and it's tied in with that fundamental force of gravity. All right, so now we're going to go ahead and graph our values. So let me read this real fast. It says, using the graphing grid below, okay, because again, you're not going to be graphing anything on the computer, you're just going to be graphing by hand, which is nice. I think it's kind of accessible, and since we're just drawing, it's just a straight linear graph, we're going to, in terms of like a diagonal line, I think it should work quite well, okay? So we're going to plot the 5 lengths. Of course, in our case, we're just going to have 3, right, for my example. And it's going to have, the graph is going to be the string length L, right, sticking with the base unit of meters, very important. We need to keep, all the same units, okay? Just at least pay attention to how they're described in the lab. On the vertical axis, so let's go ahead and label that. As I do mention that you need to label your axes, so it should look like this. So it should be length in meters, okay? And that's going to be a function of, okay, because anything on the vertical axis is the dependent variable, and then everything on the horizontal axis is the independent variable, okay? So we're saying that the length is a function of the value of t squared over 4 pi squared, okay? Actually, the period is more of a function of the length, I guess. Here, we want this relationship to have that particular value of rise over run. So, I'd say the choice of axes, honestly, is less to do with the independent-dependent idea and more to do with the fact that we want the slope to be precisely gravity instead of, say, the reciprocal, 1 over gravity, okay? Now, when I mean gravity, I mean g, okay? All right, so when I say gravity, I mean g. But regardless, you should do it this way, with the vertical axis being length and the horizontal axis being the value t squared over 4 pi squared, okay? So we'll just label that t squared. All right, kind of looks interesting here in terms of the graph not having a bottom, but we can certainly work with that. All right, so, and it's good to maybe, I give it a name. I mean, it's hard here. It's basically just a particular calculation, some values. I mean, you could say it's period squared divided by 4 pi squared, but that's awfully wordy. So here you can just leave the formula essentially, but you still do want to put the units. So in parentheses, put second squared, okay? All right, so let's go ahead and actually graph those values. You could flip back to the previous page. I'm just going to pull them off of Desmos here. Okay, so we've got our 3 lengths, which is the 2. All right, so let's kind of set the values here, right? So I want to set a scale. Let's say if I make that, okay, let's put 2 meters all the way up on top. We kind of, yeah, sure. We have it be right at the top, okay? So this would be 2 meters, okay, which of course would make this one right in the middle 1 meter. And I'll move my label over a bit. All right, so this would be 1 meter, okay? And then in between is going to be 1.5 meters and half a meter, okay? And then right here, see, because I think that should be the bottom, because let's count our squares here. 1, 2, 3, 4, 5. Yeah, because each of the larger grids is 5 by 5. So this is the 0 point, okay? That corresponds to the origin, the 0. And same thing over here on the horizontal axis, that would be 0 as well. Okay? And if we look at the range of values we got for our t squared over 4 pi squared values, they range between, right, for the longest one, that's the biggest one, it goes up to 0.2, and then the smallest one is, oh, let's undo that. I think I can. I need that back. All right. Oh, there we go. Didn't mean to delete that. Okay, and then they range between, 1.5 and 2. So if we go to 0, I mean, they're all going to be clustered in that case. So let's actually not have it start at 0. You don't have to. Let's have it start range between 1 point. If we have it be 1.4, then this could be, if you think about this, it could be 1.4, 1.5, 1.6, 1.7, 1.8. That wouldn't catch everything. But if we took steps of, say, 0.25, right? So it took steps of a quarter of 1, that could probably make things work, right? So we could just go from, that way we could just go from 1 to 2, okay? And then it wouldn't be too crowded together. You're going to have more values, so you won't have to consider this so much, but you don't want to choose a scale where your 3 points, because that's what, in my case, I'm putting 3 points in this graph, you'll be putting 5, okay? But you don't want them all to be clustered in one corner because you didn't choose a very good scale, okay? All right, so over here, I'm going to have 1, all right? And that's going to be square second. Okay, that's going to put, this one at 1.25. I'll squeeze that in here. All right, square seconds. This one over here then is going to be 1.50 square seconds, 1.75 square seconds, and finally 2.0 square seconds. All right, so now let's actually plot our points. All right, so I'll get a large pen here to draw our points. Okay, so our first one is the T1, right? I'm just going to show it to you up here. All right, call attention to it in my Desmos calculator on the left, right? That corresponds to the 2-meter string length. And so it's basically 2 and 2.1. So it's going to be right up at the top, right? Kind of an approximation. It would be nice if I had, a little bit more space. You could, kind of have it just kind of be slightly off the graph, right? So, because, let's see, because our length was exactly 2, but this comes out to be more like 2.1. 2.1 would be, so it'd be kind of like right over here, right? If we're going to estimate it, okay? All right, which is what we're doing here, because we are just going to draw a straight line. You're going to want to use a ruler to do so. If you're doing it on a tablet, you can actually take advantage of the straight line drawing tool. But let's do the next one. This is the string length, which was it 1.85, I believe. Let's double check. It wouldn't show up there. Over here, 1.85. Okay. All right, so 1.85 is going to be, okay, I guess I'm still going to have a bit of clustering, but not too much. All right, so, okay, 1.85. Let's put it right over here, okay? So it's going to be about halfway, 1.75 would be exactly halfway. So if we think of this, this is 1.6, 1.7, 1.8, all right? So, and that's 1.9, so it's going to be halfway between those two. Okay, so it's going to be on, just for the sake of helping draw this, I'll draw a straight line through here, right? Just to remind myself, it's going to be on that line, and it's going to be 1.79, all right? So 1.79 will be, again, let's check this. So this is a total change of 0.25, so that means each of these, since, is going to be 0.05, so that's 1.8, 1.85, okay? So it's between 1.75 and 1.8, so it's going to be right along this vertical line. Okay, I'll do the same sort of thing, do a little sketch. All right, just as a guide, and then there is my point. Okay, so we could say then that this is for length 1, this is for length 2, and then finally let's do our one for length 3. All right, that was our string that was only 1.5 meters long. All right, so that's going to be right along this thick line right here. All right, so no guideline necessary. And that corresponds to a t squared over 4 pi squared value of 1.5. So right here. All right, there we go. Excellent. Okay, so then this question explains that because of our choice of values, right, the very particular choice of having L be our vertical axis and our horizontal axis being t squared over 4 pi squared, that means that we have an equation of the line of this form, y equals mx. So what I'm saying here is that L is playing the role of y, all right, x, right, is being played by t squared over 4 pi squared. That means that m, the slope, is g. Nice, okay? So, and I go on and explain a bit more, and then I say sketch the line on top of your data points above and show your calculation for the slope, okay? So let's go ahead and do that. Let's choose a different color, and I'm just going to sketch a straight line that's supposed to connect all 3 data points. Now, the thing is that that's why I wanted to do more than 2, because if I just shown 2, potential lengths, then I could always draw a line that exactly went through 2 of them. But here, kind of showing more realistic data, your line is going to do its best job of hitting all 3 or 5, but it probably won't be able to hit all 5 exactly, right? Because of just, a little bit of error in your measurements, a little bit of effects that you weren't accounting for, okay? There are a lot of things that can happen that don't perfectly fit in this model. That's why we're doing averages, okay? So here I chose a line that went exactly through 3, but then got about as close to 0.2 as it did to 0.1, so I kind of averaged out. You just got to eyeball that line and do your best. Okay. So now we want to think about how we actually calculate the slope of this line, and the best way to do that is just see when it crosses over some of the major grid points. Okay. So I can see a great example of that right here. So I'm going to go ahead and choose yet another color, and I'm going to draw a triangle to highlight the slope, okay? Because the slope, after all, is rise over run, right? So this would be, right here, would be what we call the run value, which is just the change of the horizontal value, all right? And over here is the rise. And I chose, this particular size triangle because it's easy to see exactly what the values are, right? We have a rise of exactly 0.5 meters, which you can see here, okay, because it's the difference between those larger squares. And we have a run of, well, exactly 2 of the larger squares, which corresponds to, well, half a square second, okay? So let's go then ahead and show our calculation for the slope, okay? Slope being rise or run, all right, is then going to be equal to, I said it was half a meter on top, all right? And you can see here that I point out that the rise should be in meters, so didn't make any mistakes there. Good. Write this a little bit more clearly. Okay, and then our run was half a square second, so 0.5 square seconds. Okay, so you might be looking at that and say, well, 0.5 over 0.5, what are we going to get, right? Well, let's see. Okay, let's go ahead and plug that in. So if I have 0.5 divided by 0.5, right, I'm going to get a value of 1, okay? So let's see, 522, we were doing that correctly? Because I feel like maybe not, right? So because our difference was, because we should be getting a value of 10. So I'm missing a decimal place somewhere. Where is that showing up? Okay, because we went from 1.5 up to 2 for our values of t squared over 4 pi squared. Just checking for any calculation errors here. Okay, those all make sense. Okay, and then this is in meters. We stuck with, yeah, we all have everything's in seconds just fine. Okay. So yeah, we ranged from 1.5 all the way up to 2. Why would we get 1 meter per second squared and not 10? 1 meter. I must be missing something obvious here. Okay, so these were all of our lengths. Okay, basically I'm making sure that nothing is in centimeters. That would certainly explain, potentially a factor of 10. Okay, so we got our different values, and they ranged all okay. So 0.5, yeah, it makes sense, and yeah, so do those ones. Okay. Okay, so what are we looking at here? Meters per second squared. All right, so because 1 meter per second squared is not what we should be getting for gravity. We should be getting, well, the theoretical value, which I mentioned over here, is going to be, well, 9.8, okay? Right here, 9.8 meters per second squared. And then we're going to use that to make our calculation for the mass of Earth, and then eventually compare that mass of Earth to the more precisely measured mass of Earth, measured with other techniques, because there are, in fact, other ways of doing it as well. You can't put it on a scale, but you can do things about the way Earth rotates and so on, and the way it orbits, gravitational effects and so on. But let's take a quick look here. Okay, so didn't expect to have any calculation confusion. It seems like it should be pretty straightforward, but 1.5 to 2, that is a half square second difference. Okay, yeah, which is what I have there. All right, and I was dividing by, yep, that's the time for one full swing. Okay, I guess it could be that my values are a little off. Let's see, because I was doing them all based off of this, hypothetical period, right? L over G. So let's see if maybe I did that wrong. Because again, I was making up values. So let's check what a hypothetical period should be for, say, a 2 meter swing. So let's take this. We have pi, and then we'll do our square root of, so here in meters, 2, and then divided by 9.8. Okay, so 2.8 is the hypothetical time for that one full swing of the period. Okay, all right. So that's interesting. Why off by 2 meters per second? Yeah, this is precisely the correct units. Let me double check. Meters over meters per second squared. That's okay. And then in the case of having the period, let me just take a quick idea here. So we have, this comes out of basically the rotation, that partial rotation of the swing. So let me just do a quick check, make sure I don't have a typo there. So we have period of a pendulum. So period of pendulum swing, okay? Because it's I'll just double check the angular part. So 2 pi, yep, okay. I'm just checking on another device. So sorry for the delay. Let's see. Yeah, yes, it is definitely 2 pi over L over G. Okay, so those times make sense and they kind of match what I would expect. Let's do then, if we just had one value, right, which is not as sound as, drawing our slope, let's see what value of G we get. Because that would tell me if my mistake is in the slope or is it, in somewhere in these first formulas, okay? So here I'm going to have 4 pi squared, okay? And then just L over G. So we'll do 2, right? Just one example, 2, and then a period, which would be, let's say 2.83. Okay, I could have copied that over, of course, but here I just want to do an estimate. Okay, yeah, okay. So this formula is sound. Okay, so definitely is something I did. A little mistake I made with the graph, because this all checks out. This should give us a value of 9.9, right? Which is pretty close to the theoretical value, which then will get us to our mass of the Earth based on another important constant and a much more universal one, which is big G, right? Because that applies to all planets, all stars, all galaxies. It's this universal idea about how strong gravity is throughout the entire cosmos. Whereas little g is just a consequence of that applies specifically to Earth based on Earth's size and radius, okay? All right, so let's go here. So I got all the different times. All right, and then, okay, so, and then we squared all of them. Up here, 2.4, 2.6, 2.8, okay. Okay, and divided them by 4 pi squared, yeah. Is there something going on, like with this calculation? Is it not, what if I add parentheses? That shouldn't make a difference. Let's see. Yeah, so 1.79, okay. And then the difference there, oh, I think it's just, yeah, okay. It's just me. It's I'm not. I see it now because it's such a thing, right? Such a easy thing to miss, but also so obvious that maybe you were yelling at your screen and saying, oh, like, can't you see that the difference here is not 0.5? It is in fact 0.05, right? Because if you look here, going from 1.5 to zero point 0.2 is not a 0.5 difference. That's precisely it. It is 0.05. And I'll show that in the calculator. I just couldn't, kind of calculate it in my head, right? So arithmetic mistake, but I finally see it, okay? But by the way, that process of kind of going through, having a number of 1 meter per second squared for your calculated gravitational acceleration, realizing that that doesn't make sense, and in fact, it's clearly off by a factor of 10, because 10 meters per second squared is reasonably close to 9.8 meters per second squared, the expected value. That's the kind of process that you need to think about. And the way you saw me go through and kind of troubleshoot where it was coming from, making sure the equations are right, is exactly what you want to do in terms of, in your case, make sure your calculations are correct, which I also checked. Okay, but here it just came down to simple, reading the arithmetic wrong. And what I mean is if I took, say, that 2.06 and I subtract 1.47, you can see the difference is not 0.5, it is 0.05, right? Okay, cool. Now let's make a little note here, right, that this spread, okay, is, so difference of, you don't need to do this in your lab report, I just want to clarify what I was talking about. So it's a difference of about 0.5 seconds squared. Okay, so let's go back then over here. So so then here, again, we actually don't have an issue because we went from 1.5, let's see, to, yep, so that's this. So again, here it is precisely a difference of 0.05, okay, because we went from, yeah, so, well, here it looks, I think there's, maybe I drew my axes incorrectly, right, because it's 1.5 over there. Okay, well, I guess because they're all just in this region, 1.5 to 2, okay? And yeah, I guess that is in fact, wow, yeah, so it's just the arithmetic that's getting me, and that gives us a difference of 0.05. Neat. All right, and oh, I see. And in fact, I did draw it wrong in the graph. Okay, yep, because you can see here, I correctly drew it with the decimal after the 0, and then for some reason, when I copied it over to the horizontal axis, I made it all 1 and 1.25. All right, so let's fix that. So this should be 0.10. This one should be 0.125. 0.125. All right, this one should be 0.15. All right, yep, and that's why I kept confusing myself. Good, so we pinpointed what the issue was. And this should be 0.2. Same units, square seconds, and everything. All right, so that means that our value here, based on drawing that, that line that goes through as many data points as possible, has a run value of 0.05, which then gives us exactly what we need. If we go up here and put that in, of 10, right? And, it's like, I'm not trying to, make our, my made up measurements match the theory, although I suppose I am. I just, you should get pretty good data. Your data should definitely be much closer to 10 than it is to 1, okay? And honestly, closer to 10 than 5, right? So if your data says, gives you 4 meters per second squared, that also tells you something went wrong, okay? So then we're actually going to go down and, put that value, all right? So that was, the value we got was precisely 10, okay? So 10, all right, meters per second squared. Then, okay, then we're going to use that to calculate the mass of the Earth, okay? And so that's going to be using equation 4. All right, so let's go get that. So equation 4 is this one here, which is based off of now all things we know. Because this whole concept, this whole premise of calculating the mass of the Earth is based on the assumption that you know the gravitational constant, which you can find experimentally, and you know the radius of the Earth, which you can find through observational science, such as during eclipses of the moon and so on. Okay, so right, this is the formula we're going to use: m equals g r squared, right, little g r squared over big G. Okay, so let's put that in. So m of the Earth is little g, big R squared, over m. Okay, so sorry, over big G. Right? Did I do that correctly? Let's see. Yep. All right. So then let's also copy over the number for the radius of the Earth. We have that is 6,371,000 meters. I'm going to go ahead and write that in scientific notation as 6.37 times 10 to the 6 meters. So 6.37 times 10 to the 6. All right. So we have our experimental value of G, 10 meters per second squared, right? You'll probably get a slightly different number. And over here, we're going to have our 6.371 times 10 to the 6 meters, okay, squared. You want that to be in meters, not kilometers, but I give it to you, so it shouldn't be an issue. And then below, you're going to put the value for the gravitational constant, which I don't have to flip back and see because I know this one, 6.67 times 10 to the negative 11, and it'll just be Newton meter squared over kilogram squared. Okay? All right, which are all reported in the lab, right? But those are the correct units. So let's actually then get our experimentally estimated, all right? You can say experimentally measured mass of the Earth, okay? So I'm gonna go down to make that calculation. Okay, so we, our slope gave us precisely 10, so I didn't, save that value, okay? But I'll just, just type in 10, but I will call this M, all right? Just big M for the mass of the Earth. I dropped the subscript, so, because there's only one mass we're talking about here. And then we'll just, up top, we're just going to have 10, and then times 6.371 times 10 to the sixth power, all right? And then remember to square that, okay? And then we're gonna divide all of that by the gravitational constant, 6.67 times 10 to the negative 11, so it's a really small number. All right, and there we have it. So our measured value for Earth is 6.09, because the 8 would round out, because the next digit is a 5, times 10 to the 24, and it will be in kilograms, because kilograms are the base unit of, well, mass, and we've been sticking with all base units, as you want to do with physical calculations, okay? And astronomy very much uses the approach of physics, okay? And now we're actually going to put that number in here, all right? So the value of Earth that we got, right? So I'll just reproduce it over here. So 6.09 times 10 to the 24 kilograms, okay? And then you're going to calculate the percent error. How close is this to the expected value, what you call the accepted value of 5.98, right? So our percent error then is going to be the difference between the two. Trying to draw a fraction here. There we go. All right, so measured minus accepted. Now you take the absolute value of them. In this case, the measured is bigger, so we wouldn't get a negative anyway, but your percent error should always be positive. So 6.09 times 10 to the 24 kilograms minus the accepted of 5.98. We just say the more precisely measured, 24, and accepted in the sense of, like peer-reviewed science. This is, a lot of people have agreed and remeasured that number, and, they have come to that conclusion that the mass is 5.98 times 10 to the 24 kilograms. By the way, that would be a trillion, right? Because 10 to the 12 is a trillion. Okay, and then we'll just divide by the accepted. Remember, the accepted always goes in the denominator when you're doing one of these percent error calculations, not the measured. The measured does not go in the denominator. All right, and then we multiply by 100, because otherwise it would be a proportion rather than a percent. Okay, so let's see what we get for that, and I'll just not write it twice this time. I'm just going to write it down here, because that's where you want to put the percent error. All right, so let's see what we get. So we'll just take the difference between our two values. So I will take the calculated one now, because I don't want to round, right, unnecessarily. And then we'll, subtract the accepted 10 to the 24. We can see right away they are fairly close, right? They're both on what's called the same order of magnitude, which means the same factor of 10. They both have that 10 to the 24 in the scientific notation. All right, and then we'll divide by the accepted 5.98 times 10 to the 24. All right, multiply by 100 to turn it into a percentage, and that means we have a percent error, quite small, right? Remember, this is made-up data, of 1.76%. All right, and that would be it for the lab. So I hope this instructional video, including, me making a little gaffe there and having to figure out what was going on, has been informative and helpful. Thank you so much for watching.